So good evening, everybody. Welcome to Stern. So my name is Natalia Levina. I'm the director of the Fubon Center for Technology, Business, and Innovation. If you haven't heard about the Fubon Center yet or registered without noticing the center's profile, our center has launched in April of 2018. So we are, strictly speaking, right about 1 year old. The mission of our center is to support interdisciplinary work that related to the topics of technology and innovation. I am lucky to have 3 amazing co-directors of the center, 2 of whom are here. Kathleen DeRose, if you can, she's leading the FinTech part of our center. And in a minute, I'll introduce my colleague, Professor Foster Provo. And we're also lucky to have Professor Melissa Schilling, who I'm sure some of you had as your instructor, as I see many of familiar faces of my former students. And with that said, we are very fortunate to launch our new series on artificial intelligence in business, which is led by Professor Foster Provo. And this is the first of our series of talks. Today's talk, as you know, focuses on machine learning and artificial intelligence. On April 15th, in case you missed it, it's in your bookmarks. We have the next talk, which is focusing on the topic of algorithmic fairness. And in September, in case you forget about us over the summer, we will have another talk focused on the issues of artificial intelligence and the changing nature of work. You can find wonderful videos from our prior events on our website. So if you missed our FinTech conference, which was held in October, all the talks and notes for the talks you can find there. And finally, in case you really want to capture and share the great insights from today with your colleagues, we will have a full video of today's event posted in a few days. And for anybody who's registered either on site or ahead of time will receive a link to the video. So don't worry if you miss a few phrases, you'll have the video. Without further ado, I'd like to introduce my colleague and co-director of the Fubon Center, Professor Foster Provo. Professor Provo is Professor of Data Science and Information Systems. He's Andre Mayer Faculty Fellow at the NYU Stern School of Business. He is one of the co-directors of the Fubon Center. And he's also the former director of the Center for Data Science that some of you might have heard about, which is one of the early day interdisciplinary initiatives around data science at NYU. He's previously served as an editor-in-chief of the Journal of Machine Learning and was elected as a founding member of the International Machine Learning Society. Foster's research has won numerous awards. He has won most recently 2017 European Researcher of Paper of the Year Award. 2016, he won the best paper in one of our top journals, Information Systems Research. Perhaps worth mentioning as particularly important best paper award is he received the best paper award from ACM SIG KDD conference across 3 decades. So in academia, we think that's real quality when you win the best paper over 30 years award. Professor Provo has extended experience not only in academia but also in business. He's worked for 5 years in the industry after receiving his PhD in computer science. In particular, as part of that experience, he won the President's Award at 9X Science and Technology. That's now Verizon, in case people are younger and don't know what 9X is. His book, Data Science for Business, is a perennial bestseller and is used in many, many data science courses across the world and in business schools and beyond. Foster has designed and, Foster has also, oh yes, I am almost done. You have a lot of good things I could say about you. So I just want to mention that Professor Provo has designed data science architecture for a number of startups. Is that you could find them on his website, but most notable and a recent award is that CFO Tech Outlook 2019 named one of the companies he's involved with now, Deduction, as one of the biggest innovators of the year in AI. So without further ado, and sorry for a lengthy introduction, I'd like to welcome Professor Provo.
Thanks a lot, Natalia, and thanks everybody. So Natalia mentioned that we have, this is our inaugural event in our series on demystifying AI and machine learning. Artificial intelligence and machine learning, I don't know about you, but I seem to be encountering them more and more when I read the newspaper, or when I read in Business Week, or when I read just about anything. And I've been studying and building AI systems for 30 years, and I'm mystified by what the heck is this stuff is. I read articles, I don't know what the heck's going on. It seems like either, there's some dark magic that, that's sort of inside there that is going to automate away all of our jobs, as apparently some of my colleagues in business schools are telling their students, and we should either be terrified by this or anxiously awaiting all the leisure that this is going to give us. There's, some people think there's going to be cars driving themselves around the streets of Manhattan. And there's actual discussion, not just science fiction, about, when is it that machines are going to become smarter than we are? By the way, aren't they already? So, we thought we would try to do our part here at the Fubon Center to demystify this at least a little bit, piece by piece. And to that end, I have got the great pleasure of welcoming my friend and colleague, Pedro Domingos. Pedro is a faculty professor in computer science at the University of Washington, and he's head of machine learning research here at D.E. Shaw. And he's the author of the book, The Master Algorithm, how the quest for the ultimate learning machine will remake our world, which, if you haven't read it yet, read it. It's great. It was, I guess it came out in 2015, and in 2016, Bill Gates recommended it as one of the 2 books that you have to read about artificial intelligence. And I think last year, Chinese President Xi Jinping was caught with it on his bookshelf. I don't actually know how you get caught as a president of China, get caught with something on your bookshelf, but I really like that part of the story. Pedro and I got to know each other as young AI guys back in the mid-90s, when we continued to sort of work on similar topics over and over again. Pedro has won the top innovation award in data science. He's a fellow of the Association for the Advancement of Artificial Intelligence. He's received a Fulbright Scholarship, a Sloan Fellowship, the National Science Foundation's Career Award, and lots of Best Paper Awards. His papers, I tell my students, if it's written by Pedro Domingos, just read it. One more thing, Natalia mentioned this, but I just wanted to give another plug before we actually see the part of the show you came for, which is Pedro's talk. Yes, in 2 weeks we have the second installment of our series, because tonight's was postponed due to the snow day. They're close to each other. But we're going to have Solon Barocas, who's faculty at Cornell and a researcher at New York City's lab of Microsoft Research, and is one of the world's expert at the confluence of ethics, law, and machine learning. And he's going to come and talk to us about the fact, as you'll learn a little from Pedro, a machine learning algorithm is a computer program that writes other computer programs. And as increasingly the computer programs that are doing things in business and in government are actually written by other computer programs, we have to ask ourselves, what are the ethical implications? And is there even a strong ethical foundation? And this is what Solon is an expert in, and so he's going to come and talk to us about algorithmic fairness and business. And so that'll be 2 weeks from this evening. Okay, so without further ado, let me turn the mic over to Pedro, and thanks so much for spending some time with us.
All right. Thank you, everybody, for being here. Thanks, Foster, for bringing me here. It's a particular pleasure given how long we've known each other and how different things were when we started out doing AI. So as Foster mentioned, there's a lot of excitement about AI today, but also a lot of confusion. Some people, like Sundar Pichai, the CEO of Google, think it's the greatest invention in history since fire. Others think it's a bunch of hype. There's a lot of discussion, some of it quite heated. There's also a lot of people who have to make decisions, business decisions, policy decisions, personal and professional decisions that have to do with AI. And at the same time, people's understanding of AI, I think, is really incomplete and often at odds with reality. So what I would like to do in the next 45 minutes is maybe try to give a little bit of perspective on what AI really is and what it can and can't do, because I think that's one of the biggest points of confusion is what can we do with AI today and what can we not do with AI. And then I think with that understanding, then all our debates and decisions can be much more informed. So what is AI? AI is getting computers to do things that previously could only be done by humans. Well, that's a very ambitious and also very broad goal. It includes things like, for example, reasoning, problem solving, planning, acquiring common sense knowledge and using it, understanding speech and language, understanding what we see in the world, being able to navigate through the world and manipulate things, and very importantly, learning. And associated with each of these capabilities, there's a subfield of AI, in particular machine learning, which Foster and I have both worked in, is really the subfield of AI that deals with getting computers to learn. Now, there have been two major eras of AI. There was the famous AI summer, circa the 80s. And that was the first coming of AI, but it didn't really succeed. And the reason we are where we are today is that the field changed in how it approaches problems. The approach from that kind of prevailed in the 70s and 80s was what were and are called knowledge-based systems. And the idea here is that we manually encode into the computer all the knowledge that it needs to solve problems. If we wanted to do medical diagnosis, we interview a bunch of doctors and write down the rules by which to diagnose people. This unfortunately failed because of what is called the knowledge acquisition bottleneck. There's just too much knowledge, and you're never done acquiring more and more knowledge, more and more rules, and it's never enough. It's always very brittle. This caused us to change our emphasis to doing something else, and this is, started really taking off in the 90s, and then today it's really what underlies all the big successes of AI, is to do machine learning. And the idea in machine learning is that, no, we're not going to program the computer how to do things. We're going to have the computer learn from data by observing people, by trying to figure out what's going on. And this, tends to work much better, and in particular, it scales much better. Because as we get more data, now in some sense we get more knowledge for free. And as the amount of data available has been exploding in recent years, computers have started getting way and way smarter by taking advantage of it using machine learning. So this may seem like, black magic, like Foster was saying. How do computers do that, right? How exactly does a computer learn from data? Well, there's 5 main ways. One of them is to just, work a little bit like scientists using the scientific method. Fill in the gaps in your existing knowledge. Make hypotheses, test them, refine them. This is one, probably the oldest one. Another one, which is actually the dominant one today, is to emulate the brain. Your brain is the greatest learning machine the world has ever seen. So, as usual, when engineers are behind the competition, what they do is they reverse engineer it. So let's reverse engineer the competition. And this is what these days is called deep learning. It's also known as neural networks and connectionism. Another one is to simulate evolution. Right? Evolution produces amazing things like you and me, so why don't we do it on the computer? The fourth one is predicated on the observation that all knowledge that is learned from data is necessarily uncertain. We're never sure. And this is one of the big barriers. So what we should do is quantify that uncertainty and then systematically reduce it. The more we reduce it, the more we know. And finally, there's this approach of that's very common in human beings and how they solve problems, is to notice similarities between new situations and old ones, and then by analogy try to infer what to do in the new situation from the old one. And associated with each of these approaches, there's a whole school of thought, there's a whole paradigm in machine learning. And what I'm going to do here is give you just the highlights of what each one does and what some of the examples of the things that have been done with it. So the first one is associated with the symbolists. It has its origins in logic and philosophy. One of the interesting things about machine learning, or at least for my taste, is that every paradigm has its roots in a different field of science. So under the guise of studying machine learning, you can study all sorts of things and never be bored. Each of these schools also has its own master algorithm. An algorithm that you can use, in principle, to learn any knowledge from data. The master algorithm of the symbolists is what is called inverse deduction, and we'll see in just a second what it is. For each of these algorithms, there's a theorem that says if you give it enough data, it will learn anything. Of course, whether you can learn with a realistic amount of data in computing is a different matter, but at least those theorems are there. Then there are the connectionists. These are the people I mentioned who are obviously influenced by neuroscience. Their master algorithm is backpropagation. You all have it in your pocket right now, powering the speech recognition and other things in your cell phone. The evolutionaries are the people who are influenced by, obviously, evolutionary biology. Their master algorithm is something called genetic programming, or more generally, genetic algorithms inspired by genetics. The Bayesians come from statistics. They're the people who worry about uncertainty, and their approach is probabilistic inference based on Bayes' theorem, which is where the name comes from. And then finally, the analogizers, the people who see learning and reasoning as doing analogies and playing them out. They actually have a diverse set of influences, but probably the most important one is from psychology, because again, there's a lot of experimental evidence that humans do this. And the most important algorithm in this class is what are called kernel machines or support vector machines. So let's start with the symbolists. Here are three of the most prominent symbolists in the world: Tom Mitchell at Carnegie Mellon, Steve Muggleton in the UK, and Ross Quinlan in Australia. And the basic idea behind symbolic learning is actually a really brilliant insight. And this is the following. What is induction, right? Machine learning is induction, right? Is inducing general rules from specific facts. And this is a very hard thing to do. What we do, however, know very well how to do is the opposite. It's deduction. It's going from general rules to specific facts. And in the history of mathematics, people have over and over again succeeded by taking something they didn't understand and viewing it as the inverse operation of something they did understand. Like, for example, we can understand subtraction as the opposite of addition, or integration as the inverse of differentiation. So the idea here is, let us do the same thing, but with induction and deduction as the inverse operations. So for example, addition lets you answer questions like, if I add 2 and 2, what do I get? The answer is 4. That's not the deepest thing you'll hear today. Subtraction gives us the answer to the inverse question, which is, what do I need to add to 2 in order to get 4? And the answer, of course, is 2. Similarly, deduction lets you answer questions like, if I know that Socrates is human and that humans are mortal, what can I infer from that? Well, I can infer that Socrates is mortal, right? Now that's deduction, that's easy. Induction is the opposite. It's saying, if I know that Socrates is human, what else do I need to know in order to infer that he's mortal? And the answer, of course, is, if I know that humans are mortal, then I can infer that Socrates is mortal. And now I've just added the new rule to my knowledge base. And in the future, I can combine that rule, chain it to answer questions, do inferences in situations that are potentially very different from the situation in which I learned this. And this ability to learn composable knowledge is something that only the symbolists have. It's one of the most important things they have. Now, of course, this is all in natural language, and computers don't understand natural language. They do this in a formal language, like, for example, first-order logic. But the basic idea is the same. And as I mentioned, this is a little bit like scientists at work, formulating hypotheses to explain what they see, testing them, refining them. And in fact, one of the most exciting and eye-opening, I would say, applications of symbolic learning to date is precisely to automate science. So for example, the biologist in this picture is not the guy, give me a second here. The biologist in this picture is not this guy. That's a machine learning researcher by the name of Ross King. The biologist in this picture is the machine in the background. Ross is at the University of Manchester, and he's built a series of machines. The first one was called Adam, and the current one is called Eve, that are a complete scientist in a box. Very imaginative. They are a complete scientist in a box. It starts out with some basic knowledge of molecular biology, DNA, proteins, and so on. And then it's given, for example, a model organism to study, like, say, yeast. And then it starts formulating hypotheses using the inverse deduction process that I just described. And it actually designs and carries out all by itself the experiments to test those hypotheses. So what you have there are things like microarrays and you know, gene sequences and whatnot. And then based on that, it refines the hypothesis and keeps going. And recently, Eve discovered a new malaria drug that is now being tested. And once you have one robot scientist like this, there's nothing keeping you from making millions. And I imagine you're a biologist now, and instead of having 10 postdocs, you can have 10 million. And make progress a million times faster. And they don't get grumpy, they don't need to sleep, they have no rights, right? It's amazing. Now the connectionists look at all of this and say, well, yeah, but most learning is not scientists in a lab coat or mathematicians, doing deductions with, pencil and paper. Most learning is done by people in real life. And of course, the learning engine that powers all of this is your brain. So if only we could understand how the brain works, then everything else would follow. And these are the connectionists, so-called, because all the knowledge is in the connections between your neurons. And here are the three leading connectionists in the world. In fact, just last week, they won the Turing Award, the Nobel Prize of Computer Science, highly deserved. The leader of that whole school is Jeff Hinton. He's actually been doing this since 1970, since he was a grad student, against the wishes of his advisor. And he really believes that there's a single algorithm by which the brain learns, and he's going to discover it. And he's been at it for 40 years. In fact, he tells the story of coming home from work one day saying, yes, I did it. I figured out how the brain works. And his daughter looked up at him and said, like, oh, Dad, not again. So he's persistent, and and his quest has had its ups and downs, but it's really starting to pay off. In particular, he's one of the inventors of backprop, which is this algorithm that powers just about everything these days. And two other very important ones are Yann LeCun and Yoshua Bengio. Yann, who of course is right here at NYU. So how does connectionism work? Well, let's follow this process of reverse engineering the competition. Do we understand the competition roughly? We know roughly how a neuron works. So we can try to build a computer model of how it works and then assemble a network, because the brain is a network of neurons, and try to make it learn in the same way, roughly, that the brain learns. So how does a neuron work? Right? What do we need to extract from it? Well, a neuron is a really, really weird kind of cell. It's a cell that really looks like a microscopic tree. There's a trunk called the axon. This is the axon. And then it branches out. The branches are called the dendrites. And then the neuron discharges, sends these electrical discharges down the axon and out through the dendrites. And then the outgoing dendrites of one neuron make contact with the roots of other neurons that confusingly are also called dendrites. And the place where they meet is called the synapse. And these synapses can be more or less efficient at passing the current. And in particular, when two neurons fire at the same time, the synapse becomes more efficient at firing. Meaning it becomes easier for the upstream neuron to make the downstream neuron fire. And to the best of our knowledge, everything you know, everything you've ever learned is contained in the strengths of your synapses, in the connections between your neurons, and hence, the name connectionism. So here's a very simple model of this. A neuron, what it does is it takes a bunch of inputs. They could be other neurons. They could be, the pixels in the camera, in the retina. It multiplies each one by a weight. That's, how efficient the synapse is. And then if that sum exceeds a threshold, then it fires. Otherwise, it doesn't fire. So for example, if I put a picture of a cat here, it should fire because it is a cat. The output should be 1. If it's not firing, then the neuron is doing something wrong, and I need to fix it. And Frank Rosenblatt in the 50s figured out how to do this for one neuron. What people couldn't figure out for many years was how to do this when you have a whole network of neurons. Your brain is a network of 10 to 100 billion neurons. And each one of them has 1,000 to 10,000 connections. So this is just on a different scale. Now the solution to that problem was precisely the backpropagation algorithm that Jeff Hinton and others came up with. And backprop at heart is a very simple idea. Backprop, all it does, it says like, well, what I'm going to do is So the problem that I'm trying to solve is like, if my output is wrong, who do I blame? Right? This is often called the credit assignment problem in machine learning, and backpropagation is the solution to it. Maybe it should be called the blame assignment problem, right? So like, who do we blame when something goes wrong? And the idea is like, I'm going to take each neuron and each weight, I'm going to say like, if I tweak this weight a little bit, if I increase it, does the error at my output go up or down? And if increasing the weight makes the output error go down, then then I'll decrease the weight. And what I'm going to do in order to make this efficient is start at the output and figure this thing out layer by layer, based on what I've already found for the downstream layers. Which is why this is called error backpropagation, or backprop for sure, right? Because it's propagating the errors back and then learning based on that. Okay. Now, as I mentioned, backprop is used for all sorts of things these days, but probably the most famous application is still the Google Cat network. This was actually on the front page of the New York Times a few years ago. And I never thought that one day I'd see a machine learning, algorithm on the front page of the New York Times, but that's the first time it happened. The Google Cat network, was trained by looking at YouTube videos. And in fact, it was the journalist John Markoff that called it the Google Cat network. It can actually recognize a lot of, it can recognize cats and dogs and people and whatnot. But it can recognize cats better than anything else, which is why he called it the Google Cat network. And the reason for that is actually very simple, is that there's more video of cats than of anything else on YouTube, because people just love to upload videos of their cats. Okay? So the network just sat there, watched hours and hours of cat videos and other videos. You could have called it maybe a better name would be like the Google, the couch potato network. But then at the end of the day, it did this amazing thing, which is it could actually recognize things like cats and dogs, which might sound like a very easy problem to us, but it's extremely hard for a computer to solve. And now the results of this are everywhere. Now the evolutionaries, they look at this and go, well, sure, that's nice that you can tweak the weights on a brain and make it learn that way. But where did the brain itself come from? In deep learning, we actually have to design by hand the architecture of the network. And in fact, we spend a lot of time doing that. But in the case of our brain, right, the brain was designed by evolution. And we roughly know how evolution works, so why don't we simulate that on a computer? Except that instead of evolving plants and animals, we're going to evolve programs and electronic circuits and so on. Okay? So John Holland was the guy who really pushed this idea in the beginning. John Cozen and for many years. John Cozen and Hod Lipson are two more recent people in this area. So how does this work? Well, John called it genetic algorithms because they're algorithms inspired by genetics. And the idea is like this. At any point in time, you have a population of individuals, which in the case of nature, each one of them is defined by a genome, which is a sequence of DNA base pairs. For computers, they can just be bit strings because it doesn't matter how many values you have. And then each of those defines a program, and then what we do is going to execute that program on the task. And the ones that do better will receive a higher fitness score, again by analogy with biology. And then the ones with the highest fitness scores get to reproduce. You literally take two of these programs and you mate them. You create a new genome that is a crossover of the father genome and the mother genome, and that's a child. And then a few more random mutations, you do a bunch of children like this, and you have a new generation. And the thing that's amazing is that if you do this starting with completely random strings, after a few thousand generations, this actually is doing things that, in many cases, human engineers can't. The evolutionaries have actually gotten a bunch of patents from the US Patent Office for things like radios and amplifiers invented by genetic algorithms. That nobody understands exactly how they work because they don't work according to our principles, but they actually do their job better. And these days, let me skip over this. These days, the evolutionary is actually having a lot of fun creating no longer just circuits or programs, but actual hardware physical robots. So this little spider is from Hod Lipson's lab. And it runs around and runs away from you and so on. It's exciting and maybe also a little scary, right? So if Terminator ever comes to pass, maybe this is how it began. Of course, these spiders are nowhere near ready to take over the world, but they've come a long way from the random soup of parts that they started out as. In fact, the way they do this is they start by doing it in simulation. Once the robots have evolved to a point where you can actually make them, then they get 3D printed. And then in each generation, the robots that do best at whatever task or measure we're trying to optimize get to program the 3D printer to produce the next generation. Okay? So this is the state of the art in evolutionary learning. Now, the connectionists and the evolutionaries, for all the quarrels that they have between them, have something very important in common, which is they do learning that is inspired by biology, whether it's the brain or evolution. Most machine learning researchers actually do not think this is such a great idea because biology is very random, right? Who knows that it produced the optimal result? What we should do is figure out from first principles what is the optimal thing to do and then implement those on the computer. And the poster children of this approach to machine learning are the Bayesians, and of course the fundamental principle from which all learning derives for them is Bayes' theorem. For a Bayesian, if your algorithm is not compatible with Bayes' theorem, it must be wrong. So the Bayesians are the most diehard of all the machine learning schools. And they say that, they say so themselves. And part of this is because for 200 years in statistics, they were a persecuted minority. So they had to get very religious about it to survive, and they did, which is a good thing, because these days, on the back of computer power and so on, it's really on the ascendant, not just in machine learning, but in statistics as well. So 3 famous Bayesians, David Heckenman, Michael Jordan, Yuda Pearl actually won the Turing Award a few years ago for inventing something called Bayesian networks, which is a very powerful representation for Bayesian learning. So what is Bayesian learning? Well, as I said, the cornerstone of Bayesian learning is Bayes' theorem. And Bayesians love it so much that a few years ago, there was a Bayesian learning startup in London, I think, that actually created a big neon sign of Bayes' theorem and hung it outside their offices for the whole city to see. So what is Bayes' theorem? And for those of you who don't know it, and what does it do? How does machine learning based on Bayes' theorem work? Well, the idea is the following. I have a set of hypotheses that I could use to explain the world. And I don't know which one is true. What I have is some probability that each hypothesis is true. And I start out with what is called the prior probability of the hypothesis, which is how much I believe in it before I even see any data. So this is what's prior because it's prior to seeing the evidence. Okay? And then I start seeing data, and the hypotheses that are compatible with the data become more probable, and the ones that aren't become less probable. So the probability of a hypothesis given the data is called its likelihood. And in fact, this is also what frequently statisticians use. And so hopefully what happens after I've seen a bunch of data, it starts to become clear which are the good hypotheses and not so good ones. And the product of the likelihood and the prior probability is what is called the posterior probability, which is how much I believe in a hypothesis after seeing the evidence. Okay? And then I have to divide by this thing called the marginal to make sure the probabilities add up to 1, but that's not that important for our purposes. Okay? So this is a very sound way to figure out how much I believe in each hypothesis and to update it according to evidence. With powerful hypothesis classes like Bayesian networks, this is extremely computationally difficult, and a lot of the smarts of the Bayesians have been coming up with ways to make that computation viable. Of course, Moore's law has also helped a lot. And Bayesian learning has been used for a lot of things. In particular, your first self-driving car will probably have a Bayesian network, helping the car figure out, what the world is that it's in and where it is on that map and so on. But one application of Bayesian learning that we are all familiar with and grateful for is spam filtering. This was actually David Heckerman's idea. And the idea here is very simple. I just have 2 hypotheses. I'm looking at an email. One hypothesis that this email is spam, and the other hypothesis that it's so-called ham, or it's a good email. And now the evidence is the contents of the email. So for example, if the email contains the word free in all capitals, that makes it more likely to be spam. If that word is followed by the word Viagra, that makes it way more likely to be spam. This is a real example. On the other hand, if it contains your best friend's name on the signature line, that makes it more likely to be ham. Okay? And this works surprisingly well. These days, there's spam filters based on all sorts of machine learning ideas, but this was the first one, and it's still one of the most widely used and most effective. So finally, the analogizers have a very different approach to all of this. And this is the idea that, and in fact, in my experience, this is the approach that most people, most non-machine learning experts find the most intuitive, perhaps because it's what we do. And the idea is when we have a problem to solve, what we do is we find in our memory a similar problem in our past experience. And then we transfer the solution from the case that we remember to the case that we need to solve now. And the simplest algorithm of this type is something called the nearest neighbor algorithm. We'll see in just a second what that is. And one of the main people responsible for establishing nearest neighbor as an important algorithm was Peter Hart. Vladimir Vapnik created kernel machines, which are the most sophisticated algorithm, or at least of the widely used algorithms of this class. Another famous analogizer is Douglas Hofstadter, whom you may know as the author of Gödel-Escherbach. And in fact, he coined the term analogizer, and his most recent book is 500 pages arguing that everything in cognition, learning, reasoning, you name it, is all just analogy in action. So he really does believe that analogy is the master algorithm. So how does nearest neighbor work? Let me introduce that to you by way of a simple puzzle. So here's the puzzle, or a simple exercise. I give you the map of two countries. One is called Pozistan and one is called Nagaland. The plus signs are the main cities in Pozistan, and the minus signs are the main cities in Nagaland. And that's all I give you. And now what I ask you is, where is the border between Pozistan and Nagaland? Okay? Now, of course, we don't know exactly because the cities don't determine the border, but if you just look at those plus and minus signs, you can probably roughly guess where the border lies. And nearest neighbor is exactly a heuristic for solving this problem. And the heuristic that nearest neighbor follows is that a point will be in Pozistan if it's closer to a plus sign, to a positive city, than to any negative one. Okay? So for example, that line right there is the set of points that are at the same distance between that plus and that minus. Okay? Very simple, but incredibly effective. In fact, what Peter Hart did back in the 60s was prove that despite the simplicity of this algorithm, you could learn anything with it given enough data. So you could actually say that this was in some sense the first real machine learning algorithm. The first algorithm that could learn without limit as you give it more data. Prior to that, there were only statistical algorithms like various kinds of linear classifiers that could only learn so much. And nearest neighbor was really the first full-blown machine learning algorithm. And it's very successful for things like medical diagnosis, for example. You need to diagnose a new patient. You know nothing about medicine. If you have a database of patient records, you can just find the patient with the most similar symptoms and assume that the diagnosis is the same. As dumb as this is, you give it a database of a few hundred cases, and it will probably beat human doctors, at diagnosis of that problem, even after all the years in med school. Makes you want to cry if you're a doctor, but hey, I hope none of you are doctors or a patient. Yeah, I mean for patients it's good because now medicine could be much cheaper and continuously available on your smartphone and so on. Nearest neighbor has some shortcomings that are solved by kernel machines, but let me skip over that. It's a very widely used type of learning, and has been for decades. Probably the most famous and economically important application of this type of learning is recommender systems. And the big insight in recommender systems was the following. Suppose I'm Netflix and I want to recommend a movie to you. In the beginning, people were trying to do it using the characteristics of the movie. What genre? Do you like action or do you like drama? The actors, like the directors. But taste is a subtle thing, and that doesn't work very well. The important insight was when people said, no, what I'm going to do is I'm going to find people who have similar tastes to yours. I'm going to find your nearest neighbors in taste space. And then if they like the movie that you haven't seen, then, then I'll recommend that to you because, since your tastes are similar, you'll probably like it as well. How do I decide how similar people are? Well, that's why you give them all those, star ratings for. If I tend to give 5 stars to a movie that you give 5 stars to and vice versa, then we have similar tastes. And, your nearest neighbors in taste space could be in China or New Zealand, it doesn't matter. If they tend to, like or dislike the same things, then I can make predictions based on that. Recommender systems are reportedly about 1/3 of Amazon's entire business, meaning 1/3 of the things they sell come from the recommendations. And for Netflix, it's 3/4. So 3/4 of Netflix's business comes from the recommender system. And of course, every e-commerce website worth its salt, not to mention the likes of Spotify and Pandora and, et cetera, they all use this. Okay, to summarize. We met the 5 main tribes of machine learning. We've seen that each one of them has a problem that it solves better than all the others. For the symbolists, it's knowledge composition. For the connectionists, it's credit assignment. For the evolutionaries, it's discovering structure. For Bayesians, it's handling uncertainty, and for the analogists, it's reasoning using similarity. And we've also seen that each one of them has a master algorithm. An algorithm that in principle is capable of learning any knowledge from data. And the more optimistic members of each of these tribes, these days probably most prominently the connectionists, they think that they have it all, right? You're going to learn everything using backprop. But most people in the field do not believe that. And the reason is simple, is that these 5 problems are all real. And each of these algorithms only solves one of them. But we're not going to have a true master algorithm until we have an algorithm that solves all of those 5 problems at the same time. So the question becomes, can we unify all these algorithms into a single true master algorithm that really does solve all those 5 problems? And at first, this seems like a really hard problem. In fact, some people used to say that it was impossible, because superficially, these algorithms look so different. Like, how could you possibly unify them? Well, in reality, once you notice that they are all made of the same 3 components, then it becomes much easier, because if you unify each of those components, then you're done. So what are those components? Well, the first one is representation. Representation is the choice of language in which you represent what you've learned. So in humans, it could be English or Chinese or another natural language. For programming, it's usually things like Java and Python and whatnot. In AI, we tend to use more abstract languages like first-order logic, which I already mentioned, or graphical models, which include Bayesian networks as a special case. And if we can somehow combine those 2 into one, right, first-order logic and graphical models, then we actually have a representation that covers all of the things that we've talked about. And in fact, a number of ways of doing that have been developed. The most successful ones are what are called probabilistic logics, which, as the name implies, have an element of probability and an element of logic. In particular, Markov logic networks, which are probably the most widely used one, are just formulas in first-order logic with weights attached. If you really believe in a formula, then you give it a high weight. If not so much, then you give it a lower weight. And then the state of the world is more probable if more formulas are true in it than formulas with higher weight are true in it. Okay? So this is the basic idea. Now the next question is, well, if I have a representation, now how do I decide what is a good versus a bad hypothesis in that representation, right? I need some kind of objective function, some kind of scoring function to decide what's good and what's not. And people here have used all sorts of things, but most of them are special cases of the posterior probabilities that Bayesians use. So in some sense, we already have, this is the easiest part of the problem, and we largely already have a solution to it. More generally, however, the evaluation function should actually not be a part of the algorithm. It should actually be something that is provided by the user. If you're a company, for example, this could be some measure of return on investment or the click-through rate if you're in the ad business. If you're a user, right? Maybe this should be some measure of your happiness, like how much you liked the movie or the song or whatever. And then what the algorithm does is it takes that measure and finds the hypothesis that optimizes it. Which brings us to the last problem, which is optimization. It's finding in that space the hypothesis that maximizes the evaluation function. Okay? And here there's a natural combination of ideas from the evolutionaries and from the connectionists. Remember, a formula in first-order logic is just a tree of sub-formulas combined by and or and not and implies and so on. So we can discover it using genetic programming, right? We have a genome that has different possible formulas and we evolve it that way. But then, of course, our formulas also have weights. But to learn those weights, we can use backpropagation. Backpropagation through the chains of reasoning by which we solved problems and answered questions in the past. And so at this point, we have something that looks pretty close to being a unification of all the 5 master algorithms. Now, does that mean that we're done? Well, some people, again, the more optimistic ones, believe that we are close to being done. I actually don't think we're anywhere close to being done. And I think the problem, or one main problem, is that there are very important ideas in machine learning that haven't been discovered by any of these schools yet. And in a way, it's harder for us, the specialists, to figure that out because we're already thinking along the tracks of a particular paradigm. So I actually have more hope that the answer will come from people outside the field. So if you have any ideas, please let me know so I can publish them. So to conclude, looking forward to when we have such a universal learner, what will it make possible that is not possible today? For example, we would all like to have a home robot that cooks dinner, does the dishes, makes the beds, maybe even looks after the children. Why don't we have that yet? Well, first of all, you can't do it without machine learning. I think there's universal agreement about that. But second of all, a home robot, in the process of a normal day, encounters every one of those 5 problems. And therefore, it needs an algorithm, a learning system that can handle all 5. And until we have that, we won't have home robots. Here's another one. Wouldn't it be nice if when you go on the web, instead of typing in some search keywords and seeing some pages that maybe are relevant, you could actually just ask questions and get answers? It would, and in fact, Google, Microsoft, Facebook, etc., they're all trying to solve this problem. Turn the web into a big knowledge base that you can then just answer, ask questions to. But of course, in order to do that, first of all, you need a very powerful representation at the level of first-order logic, otherwise it's not going to be very good. But then, the web is full of contradictory knowledge and noise and, ambiguities and whatnot, so you need probability for that as well. So again, until we've unified those 5 algorithms, we're not going to be able to solve this problem. Okay? Here's another one, perhaps the most important one, curing cancer. I've already mentioned that machine learning algorithms are very good at medical diagnosis. In fact, typically better than the human doctors at any one medical diagnosis problem if they have, the right data to train on. But we certainly have not cured cancer using machine learning. Why is that? The reason is that cancer is not a single disease. And therefore, there will never be a single drug, or very unlikely that it will ever be a single drug that cures cancer. Every patient's tumor is different. And so everyone needs a different cure. And the solution, researchers increasingly believe, is a machine learning system that takes in the patient's genome, the cancer's mutations, the patient's medical history, and then predicts for that patient what is the drug that is going to cure that cancer. Okay? But again, in order to do that, you need to understand how cells work at a very fine level. And there's an enormous amount of research going on in this, using a lot of data from things like microarrays and sequences and a lot of very advanced machine learning to do this. But we're not there yet. And again, we won't be able to do this until we solve all of those 5 problems because they're all very much present here as well. And finally, going back to recommender systems are part of everybody's life these days, right? You continue using recommender systems even when you might not realize that you are. For example, Facebook, right, is choosing what posts to show you. Twitter is basically a big machine learning algorithm figuring out what tweets to show to whom and so on. Amazon, Netflix, et cetera, et cetera. But each of these recommender systems is not that great yet. And one big reason for that is that it only knows a sliver of you, right? So Netflix knows your taste in movies, but that's it, right? And Spotify knows your taste in music, but that's it. What I would really like to have as a consumer is a recommender system that learns from all the data that I ever generate. And then it has a 360-degree picture of me. It knows me really, really well. It knows me better than my best friend. And then based on that, it can recommend things for me, at every step of life. Small things and big things. From, like what to eat today, what restaurant to pick, to where to go for college, where to move, right? These days, even things like, a third of all marriages in America today start on the internet. And the matchmakers are machine learning algorithms. We used to have village matchmakers, but now the village matchmaker is a machine learning algorithm. So there are so there are children alive today who would not have been born if not for machine learning. But if you ask the parents, like, how did you get paired? It was the algorithm, right? This is the world that we live in today. And the truth is, for all that the CEOs of those companies say, their matching algorithms are not very good. Largely because they don't know that people, like you fill in a form and somehow you match people based on that. That's not going to work, right? If you're going to entrust such an important decision to an algorithm, it had better know, for example, your taste in music. Maybe people with taste in music are more compatible. Like where you've traveled to, like your entire life is potentially relevant. But then in order to do that, even supposing that you've pooled all that data and you've dealt with all the privacy and data security problems, which is a whole, a nest of worms in its own, right, then you still need an algorithm that can actually combine all of that data into an integrated picture of you. And all the big tech companies are trying to do this, right? You see them in the virtual assistants, right? Like Siri's trying to do this, Cortana's trying to do this, Alexa, Google Now, but we don't quite have the learning that is able to do that yet. But if we do, manage to create the master algorithm, then we will, and I think we will all have, happier and more productive lives for that. Thank you.
Thanks so much, Pedro. We thought we'd spend a little bit of time. We were going to put actually a picture of fire up there for our fireside chat, but we didn't.
We can put up the picture of the, the series.
Yeah. So, so in the spirit of demystifying, by the way, thanks. I thought the talk was great. I don't know about you guys, but who cares? I'm just kidding. So when you're dealing with people out in the world who really need to know more than they do about machine learning and AI, what do you think is the key? Well, what would you be if you could fix one thing that people didn't understand? What would that thing be about AI and machine learning or whatever you want to?
Great question. And in fact, I think there is a very clear candidate for what is the single biggest and most harmful misconception that people have about AI, and it's very simple. People confuse artificial intelligence with human intelligence. We are always projecting onto AI's human qualities, like free will and consciousness and emotions and the will to power and a whole range of things that AIs just don't have. This is natural. Right? Because human beings, as I was saying, reason by analogy, and we're faced with a new phenomenon. We always try to reduce it to the ones that we already know, and human or animal intelligence is the only one that we know on the planet. But as a result of which, we tend to treat, for better and worse, AIs as if they're kind of like humans, which leads us into a lot of areas about, first of all, what they can and can't do, about what the dangers and opportunities are. And in a way, if there's only one thing that I hope people would come away from, a talk like this or from reading the master algorithm is like a much better picture of what AI really is. It's not a human being in disguise, right? There's no homunculus inside that computer system. Intelligence is just the ability to solve problems, and we solve problems, and learn to solve problems using the kinds of techniques that we discovered. And in some sense, there's no black magic there, right? Those of us in the field know that there's no black magic, even though it looks like black magic from the outside.
So I kind of joked at the very outset, like, aren't they already smarter than we are, right? And so there certainly are ways at which the AI systems are far smarter, dimensions along which they're far smarter than we are, and dimensions along which they're essentially stupid.
Yeah. In fact, what's the dimension along which the machines are the farthest ahead of us? It's in doing arithmetic. Right? We don't even give them credit for that, but a machine can beat a human at arithmetic by a factor of, 1 billion to 1 or 1 trillion? And of course, these days this isn't even measured, but remember, computers started out as a job description. There were people whose job was to compute. And it was considered something that required, a certain level of education and intelligence to just, do the math correctly. And now we don't even pay attention to that anymore. Right? And so, when people say like, oh, when will machines be smarter than people? Well, in some things, they're already way smarter. In some things, they are now becoming smarter than people. And in some things, they are very, very far from being, as smart as people.
Yeah, and so we can start to think about, I'm going to ask some questions about jobs, but we can start to think about what types of problems you might expect the computers to do really well. I mean, some of the earliest applications of machine learning and AI to business problems were things like credit scoring, right? Where it's very important, of course, to estimate the probability of default, right? And people are absolutely miserable at estimating the probability of anything, right? But once you have lots and lots of data, it's just arithmetic, And so those would be areas where it wasn't just that you could replace people because the machine could automate their job, automate them away, right? Decades and decades ago, the machine would just blow people away at doing things like estimating what's the likelihood of somebody defaulting.
Here's something that people in the field of AI in the beginning got very wrong. And in fact, a lot of people today still get wrong because it's a very natural mistake to make. But now we really know better than that. And this was the notion, kind of like very intuitive maybe, that the first jobs to be automated will be the blue collar ones. Because, those are, anybody can do those jobs, right? Whereas, like doctor, lawyer, tax accountant, right? Those take, college degree, right? Actually, it's more like the opposite, right? It's much easier to automate the job of a doctor or of a financial advisor than it is to automate the job of a construction worker. We are very far from having a robot that can walk around the construction site not tripping over itself, let alone actually doing something useful. The reason this is counterintuitive is that evolution spent 500 million years evolving us to be competent in the physical world. And we are really good at it, and we take it completely for granted. Whereas the things that you have to go to college for, those are the things that evolution did not spend any time evolving you for, and therefore we're really beginners at that. And so computers can blow past us in that very, very quickly. So the real division is not so much blue collar versus white collar as, is it a routine job versus is it a job that requires a lot of flexibility? If your job is something fairly narrowly defined and where there's a lot of data, for that, machines can probably learn to do it well. As a rule of thumb, the more of your brain your job uses, the safer it is. Because if it requires a lot of common sense knowledge, a lot of integration of information from different sources, a lot of combining abstract thinking with manipulating things in the real world, this is what is well beyond the capability of computers and will probably continue to be for the foreseeable future.
And in blue collar work, right, it was really the work that had been processized, right? I mean, like assembly line work, and so on, where somebody had laid it out and made it systematic, and so you didn't have to move around a lot, right? And that's where the robots sort of
the more flexible,
displace the human.
The more flexible your environment is, the harder for robots. In fact, industrial robotics is a classic example of this. Industrial robots work to the extent that they do because a factory is a highly controlled environment, whereas the home is a highly uncontrolled environment, right? Which is where it's very hard for homebots. But maybe an even better example of that is, transportation. We already have robots that fly planes, right? In fact, human pilots, forgive me if you're a pilot, but they're mostly superfluous these days, because an airplane in the air is actually a very simple environment. Driving a truck on the freeway is actually much more complicated. But freeway is still not a very variable environment, and this is where the frontier is. Like these days, we actually have, I think, we will have self-driving trucks that drive maybe on the freeway, not on the city, coming online fairly soon. But driving a car in the city, like in Manhattan, with everybody, honking at you and pedestrians running in front of you and whatnot, that's, a whole different, degree of chaos and variability, and, we're not there yet.
Yeah, so let's talk about that, because that was another thing I started out with. And
the Turing test of self-driving cars is driving in Manhattan.
Yeah, so, right, so when will we see self-driving cars en masse, not little tests, right, en masse on the streets of Manhattan? In our lifetime?
They're already everywhere, right? It's just that the drivers are robots disguised as humans. Well, it's April 1st, so. Well, this is a very good question, right? So let me give you 3 answers to this. The Waymo answer. The Waymo answer, right? Waymo is like, the company that is the leader in this. They're very confident. They say, any day now. Surprisingly confident, in my opinion, but hey. At the other end of the spectrum, there's people who say, not in our lifetimes. Now, the reason to say not in our lifetimes is everything that we've been talking about, right? The reason Waymo is confident is that actually they're not confident, they're not pulling it out of thin air, is the successes that they've already achieved in a lot of this kind of smaller tests and retirement communities and so on and so forth, right? Exactly how long it's going to take is actually, there's a lot of wild cards there. My personal opinion is the following. Driving a car in the city is what is called an AI complete problem. Meaning, to solve that problem, you need to solve every aspect of AI. It's not just the vision and the control, it's the tactical driving. The thing that really defeats self-driving cars is interacting with humans. Right? It's like humans are very unpredictable, and they will play, games of chicken with you, right? And people being in self-driving cars, at first they're weirded out and scared, but 10 minutes later they're just bored. Because the self-driving car is like a grandma. It's it drives very slowly, obeys all the laws. Nobody obeys all the traffic laws, but self-driving cars have to, right? So this is one aspect, right? But the other thing to realize is that the world will. So this is an argument for it's going to take a long time. But an argument for it's going to happen sooner than you think is that cities are not going to stay unchanged while self-driving cars evolve for them as they are now. Cities will evolve to meet self-driving cars in the middle. Just like they evolved to meet horseless carriages and trains and everything else. Right? We're going to set up the environment in ways that make it easier for the self-driving cars. There's going to be guides on the streets, maybe cops will have, they'll be talking, in RFID, like, not themselves, by voice, but there's going to be all these ways in which we make things more adapted to self-driving cars. So, it's an interesting question. I think it's not going to happen very, very soon, but I think it will probably happen in our lifetimes.
It's already starting to happen, rationalization of streets.
With the what, I'm sorry?
The rationalization of the streets here in New York is already easier to navigate.
Easier to navigate. So one of the things, let's go back to the other humans issue, right? I think that,
By the way, sorry, let me interject something.
Please.
The whole problem is those pesky humans.
Yeah, it's the pesky humans.
Back in the 90s, there was this test that was done in California where they took a section of the 5 freeway, that's the freeway that runs all of California, and they gave it over to self-driving cars. And those self-driving cars actually have almost no AI. They followed magnetic guides that were installed, and they kept a certain constant distance, between the car in front of them. And the test worked. It all went fine. Now the problem is that once you mix those with people, all hell breaks loose. So.
Yeah. So when the horseless carriage replaced the horse carriage, right? And you were a pedestrian, run for your life, right?
Exactly.
Nobody knew what they were doing, right? It'd run you over. The self-driving cars are going to have to be much safer than a human behind the wheel. Forget about the fact that they could be. They're going to have to be, because as soon as they plow over some idiot pedestrian, right? Then everybody starts rethinking whether they should be on the streets or not, right? But of course, people are people, and as you mentioned, why don't we all out there just walk out in front of the cars, right? This isn't Seattle.
That's
where Pedro's been living, right? Where people stand on the corner and wait for the light to change to say walk.
They'll actually wait for you to cross the street before you even get to the pedestrian crossing. Right, which makes no sense. But for self-driving cars, this is good. There's also the guy the alien in the Hitchhiker's Guide to the Galaxy, right? Who lands and walks into the middle of the road, and waves to a car saying take me to your leader, because they think Earth is the intelligent creatures on Earth are are cars, right? And then of course the poor alien gets run over. But
the reasons that we don't are some combination of law-abidingness. The fact that we really don't want to get run over by a car, and that we have some social compact with the driver that we're not going to make the driver slam on his brakes and not to hit us, right? But if we know that car is not going to run over us because it can't, or else its company is going to go out of business, right? And they haven't gone and basically made it a capital crime to jaywalk. And the person sitting there is reading the newspaper in the back seat, and it's raining, and you're basically they can wait.
The car on the one hand doesn't want to run you over, right? Because that would be bad. On the other hand, for them to be taken up, right, it has to think about the passenger, right? And there have been all these studies done by now, should the car swerve and kill the driver in order to save a poor child, standing on the street? And people say yes, right? But then they say what if it's my car? Then they kind of no. Right. So what's going to happen, right? So this is my forecast is, there will have to be laws, right, that say, the car has to stop for, to save the people. But then there'll be hacks, right? You'll buy them in the aftermarket that, you hot rod your car to not stop, right? Because people will still be people, right? Without self-driving.
I'm sort of going to get that and this is another plug for our session in 2 weeks, right? There are all of these ethical puzzles, that we learned in college in our, ethics class, and back then they were just puzzles. Do you push the fat person off the bridge in front of us to stop the trolley from running some people over?
Trolleyology, right? It's called now.
Trolleyology. Right?
There's the whole field of debating this called trolleyology.
But guess what? Once you're programming this stuff into the car, right? It's in there. Whether you know it or not is another question, like whether the machine learned it, but it's programmed in there, right?
Now,
And so,
here's something that I think is going to be very interesting about this process is that in the, computers at the end of the day are computers, right? In the process of making computers be ethical, we're actually going to have to figure out what we think about our ethics, right? It's like, we can say like, oh, we're going to give them the 3 laws of robotics, right? Popular notion, right? But people forget that every one of Isaac Asimov's stories in that series was about how they failed. Right? Those laws are too general, too generic, right? So that, encoding, the rules of ethics is not going to work, right? You could say, well, let's take the machine learning approach and have them learn to be ethical by observing us, right? But then they're going to get very confused, right? Because we don't follow our own rules of ethics, right? Very, very far from that. So this is going to force us to confront what are ethics really? So there's a lot that we've been getting away so far that we won't when we have to program the machines to be ethical.
So I think I agree with you. Is what we'll probably see in the not so distant future, right? Is going to be robotic semis on the freeway, right? Because the freeway is already off limits to pedestrians. It already has much more straightforward kind of rules of the road, it's much easier to change those rules of the road, right? And so. You heard it here. Buy up property around the freeway exits near big cities. Buy it now, because guess what? That's where all the robot trucks are going to have to stop, and then everything's going to have to get transferred over to the local trucks, which are going to need people anyway right now to unload and load the trucks wherever they're going. Right.
I mean, I don't know, this is an interesting idea. I don't know if they will get transferred, but I think this mode of like the truck is driven by a human from its starting point until the start of the freeway, which is only 30 minutes. And then the next many hours on the freeway, there's a robot driving the truck, and then somebody hops on at the end. This, I think, is actually a very good example of how, I think a lot of the story in the next, in the coming years is going to be how the division of labor between humans and AIs happens. And a lot of it is going to be, very subtle, and it's going to be worked out industry by industry, job by job. In fact, I think everybody should be working out what parts of their, the way to keep your job safe is to automate it yourself. And then you can move on to doing the interesting parts, and and actually do the whole job better, faster, cheaper, because you now have the AI doing the work for you.
So let's not think about physical robotics. Let's think about cognitive sort of AI. What jobs are ready to be automated away? I mean, actual jobs. A lot of my colleagues around here talk a lot about the future of work and how AI is going to automate away jobs, and I'm having trouble seeing what exactly are these jobs.
I don't know why there's this. This is certainly a big meme these days. Is like how AI is going to be a jobs apocalypse. And the thing is that to think about is we've had that worry every decade for the last 200 years. Right? 200 years ago, 98% of Americans were farmers. And then, the McCormick Reaper did with one person what took 50. 98% of us are not unemployed now. Right? Any change in jobs that AI is going to cause will be insignificant compared to that. What happens is that today there's people doing all kinds of jobs that you couldn't even imagine back then. Like, web app developer. Who could even explain that to someone circa, 1850, right? So I think, number one, there'll be a lot of new jobs that we don't even imagine. But number two, right, we can learn from our past experience that, people thought that ATMs were going to cause, a huge surge of unemployment in the banking sector. Actually, the end result of that was that there were more bank tellers than there were before. The difference was that people no longer went to the bank teller to get cash. For that, they had the ATM. The bank teller could do things now like give people advice, upsell them on other products. And so there's actually even, more jobs for that than before, right? And tax accountants became tax advisors, right? Now the software actually does the accounting. And I think this is going to be the case, almost across the board. This is not to say that, the unemployment profile, isn't going to change. But I think this notion that, AI will lead to mass destruction of jobs, it goes against, I'm puzzled as to why so many, even, Nobel laureate economists are so worried about this. Because what happens when you make something cheaper, right? You make the complements more valuable, right? And like, what AI does at the end of the day is make intelligence cheap. right? It's machine learning makes prediction cheap, right? There's actually economists that have studied this, right? And so the complement to that are jobs that people can do that maybe now are too expensive to do, but now will become feasible. For example, right, like recommender systems, right? If Amazon needed a human recommender figuring out, what to recommend to each one of us, this just would not be possible. But because it is possible, now there's all the other Amazon jobs that exist on top of that layer that's automated. And I think the main story of the next 10 or 20 years is going to be this, is that yes, there will be a lot of automation, but no, that will not cause mass unemployment.
So I'm going to ask one more question and then maybe open it up and see if anyone in the audience has questions. And that is, on the other side of the coin, are there things that, that maybe people don't expect are closer to happening because of AI?
Yeah, I'll give you a couple, and I hope to not break your heart. But one of the things that I keep hearing people say is, oh, yes, we can automate intelligence, but there are two things that cannot be automated and people will always be better at, or will be better for a long time. Emotional, social relationships, social intelligence, and creativity. Right? This is a very common notion. I would say misconception, but let's just call it notion, right? Now, unfortunately, or fortunately, I don't know, the news is those are actually easier. Actually, emotions, we value them very highly, right? Because that's what we're all about. And cognition exists in service of emotion. But emotion is much simpler than cognition. It's much easier to have a robot fake convincing emotional behavior than to have it do something intelligent. Much easier, so much easier that in fact it's already the case today, right? Tamagotchi, those little, pets, right? That's all they do is fake that they're hungry or that they're sad, and then you're hooked, right? No intelligence is required. I'll give you an even better example, a contrast between two bots, Cortana and Jawwise. Do people here know what Cortana and Jawwise are? They are both bots from Microsoft, okay? One of them is a huge success, another one is, mostly a failure, right? Which is which? Cortana, right, is a virtual assistant that is supposed to be competent at, answering your questions, helping you schedule things. Every time it messes up, you get annoyed with it. So Cortana requires, intelligence, right, in the AI sense that we've been talking about. Not very successful so far. Jawwise is this amazing bot that, it's in China today. It started out as an interface to Bing, right? It's a text-based interface, but then they gave it this persona of a teenage girl, right? And then they started maximizing engagement, which people are very good at doing these days with machine learning, right? And so what happens with Cortana is that sometimes she's kind of like commiserates with you, sometimes she gives you a hard time, and people get completely hooked on her, right? So Jawwise has tens of millions of users in China today. A quarter of them have told her that they love her. This is today's AI, right? It's got all the emotion you might want to ask for. Another one is creativity. Right? People think creative is like this magical thing that happens, right? Foster and I both, have been involved in music, and it's like people think like composing a song is some piece of deep magic. Actually, it's not. And in fact, there is today already very good music composed by computer, very good, paintings made by computer, things in various fields that anybody would call some of the moves of AlphaGo or even Deep Blue. If they had been made by humans, would have been, considered signs of extraordinary creativity. Let me just give you one example. David Cope is a professor, now emeritus at UC Santa Cruz of music and composer, who at one point, and this was like, 20 years ago or more, right? It's like not even recent. He got interested in, how well can computers compose music? So he has a series of programs that will compose music, according in the style of the composer of your choice. So you say, I want Mozart, and they will create a Mozart piece for you right there on the spot. And I actually saw him give a talk at AAA, I don't know if you were there, right? Where he gave a test to the audience, says, like, I'm gonna play 3 pieces. And I want you to tell me, which one is by the real Amadeus, which one is by a human composer imitating Mozart, and which one is by my program. Okay, and then people voted, right? Now the winner, was still, Mozart, okay, that's good. But by a large margin, his program beat the human composer. And honestly, if you listen to that music, whether it's in the style of Mozart or Bach or Beethoven, it's perfectly creditable music. And of course, these days in the music industry, a lot of the composition, arrangement, tweaking things is already done by machines. And there's like these companies that will, for film, you run the screenplay through their NLP system, their language understanding system, and it says like, oh, I think, if you change this character from male to female, the movie would gross another $200 million. And if it happened in this city and they had that plot twist, right? And then they use it. Of course, the creative types in Hollywood hate the guts of these systems, right? Not just because they endanger their jobs, but because like they're the opposite of what human creativity is all about. Right? But on the other hand, if you're a musician and you're not inspired that day, maybe having such a system help you would be a great thing to have. So there you go.
So with the music composition, I remember that they wanted, so in AI systems, a lot of times you want to get experts to also evaluate how well you're doing. And so they had, I think it was Bach, and they were basically seeing whether they could tell the difference between Bach and in the program. And they actually couldn't do this because the experts had heard everything by Bach. So basically, if I haven't heard it before, then it must not be.
What they should have said, they're done in the spirit of the tune, says like, we've just uncovered, this beautiful composition by Bach.
Yeah. All right. So maybe we'll see if anybody has any questions. And I've been told that you need to use the microphone because things are being recorded.
Hi.
Check, check.
Hi, thank you. I just have two questions. The first is, you mentioned a third of the matches are made on the internet. I would ask then, what percentage of internet matches versus old-fashioned end up in divorce? Can you do a study of that? And the second question is...
So let me answer your first question first. So it's not just a third of matches, it's a third of marriages, right? Start on the internet. And like the paper that first said this came out like over 10 years ago now. And at first people thought it was a fluke. But number one, so there's been a lot of follow-up, as you can imagine. It's been confirmed that this is the case. And number two, it leads to fewer divorces.
Oh, really? From the internet? Or
yeah. I mean, again, I think this is all still evolving. But, the evidence so far is that actually, finding someone on the internet is better than randomly finding them in a bar or, through your friends or whatnot.
Okay.
Which maybe is not too surprising at the end of the day because, and again, this I think is a good example of what AI does for you, right? Of course, the algorithms that are doing this are still not very intelligent at all. On the other hand, the universe of people that you can be matched with is orders of magnitude greater than it was before. And when you look at the trade-off between these two things, the great universe tends to win. Also because this is important and people are very patient. They're willing, there was this beautiful cover story in Wired, a year or two ago, of this guy who's a hacker, right? And he actually went and, downloaded the entire contents of OkCupid, right? He wasn't supposed to, but he figured out how to do that, right? He's a hacker, right? And then he went and applied machine learning, clustered the women left and right? Did all of this. And then he went on 100 dates. Failure, 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 failure. The 100th date, or, give or take, he found the love of his life and married her. Right? So the story has a happy ending, right? What are the morals of this story? Like, people, are willing to put a lot of effort into this, right? And second of all, what he was doing is what everyone will be doing without having to do the machine learning themselves in the near future. So the larger universe, that's a given, but the algorithms are getting better. And again, the percentage of people who meet online is climbing higher and higher. And hopefully the results will be better because they will be people who are less likely to get divorced, for example.
But for those of us who don't hack OkCupid?
Oh, OkCupid he used it because it was the easiest one to get the data from. They actually they were kind of like more of an independent company. This is actually funny. The guy who was one of the co-founders of OkCupid was actually part of this, band called Bishop Allen. Don't know if you ever heard of Bishop Allen, fun band. But then he wrote a book about what he found called Deduction. And it's a great read because it's all about how people say they like one thing, but then they like another, right, and so on. So.
And the second question is Alexa of Amazon considered AI?
Good question. So Alexa is continually evolving, right? The first Alexa had, so the thing that drove Alexa in the beginning was good speech recognition, which is AI, and very much an application of machine learning. And the fact that they could do what is called far field recognition, which is pick out somebody's voice even when they're not right on top of the microphone, right? So there was a lot of machine learning involved at that level. But here's the thing, like Alexa, as you've used it, has no brain, right? There is no intelligence there. Again, very good example of what I was talking about. We see Alexa interact with us and we start to think that there's some kind of virtual assistant there. I'll give you a good example that my son discovered, right? Kids are often the people who really, get into Alexa. One of the fun things that Alexa can do for you is ask you riddles, right? So you ask you a riddle, you give the answer, she says no, and then finally, hopefully you get the answer. Now what happens if you ask Alexa one of her own riddles? She doesn't understand the question. It's not just that Alexa doesn't know the answer, she doesn't even know what you asked. And the reason is that Alexa is actually several thousand so-called skills, each of which is independent of the others. So Alexa has a skill where it asks canned riddles and then has some intelligent, semi-intelligent speech understanding to see whether you answered it correctly. But that's it. It relates in no way to anything else that Alexa is doing. So right now Alexa doesn't have much of a brain. But the folks at Amazon understand that this is an important thing to have, and there's very much an all-out race between them and Google, and Apple and Microsoft. So Alexa so far is not very intelligent, but these assistants are going to rapidly get more intelligent. I think one of the great test cases of how far far and fast AI is progressing. One of them that we already talked about is self-driving cars, but another great one is virtual assistants. In terms of the economic value and how much these companies are willing to plow into it, it requires really fundamental AI research, right? It's not something that you can just engineer. But the value of that is enormous because if you create the first truly smart virtual assistant, you will be the linchpin of the world economy because everybody will use it. I think there will come a point at which we won't know how we ever lived without our virtual assistants. If you already feel that way about your smartphone today, this is going to be of a different order of magnitude. And conversely, everybody who wants to sell you something is going to have to sell it to your virtual assistant first, because your virtual assistant is the gatekeeper to you. You know how drug companies, promote drugs to doctors because they're the ones who make the decision. Everybody's going to have to go through a virtual assistant.
What is a virtual assistant?
Well, it's Siri, right? Like you can pick up, your iPhone, for example, say Siri, what is the weather today?
The question is what will be a virtual assistant, right? Example for me. I get so much email that if I read my email, I would do nothing else all day and I still wouldn't read all my email. So I have a great way to deal with that. I just ignore it. And when I finally realized this, right? Oh my God, my life changed completely. I was finally free of this thing. And when I think back of it, it's impossible for me to actually do this thing. So why was I ever actually worrying about it? Basically, anybody can send me stuff with no cost whatsoever to them, and somehow or other I should be obliged to then respond to it. Right? However, this leads to problems, like for instance, if your funding agent sends you an email and somehow or other you just ignored it, right? And so so I need this assistant to be able to actually solve that task. I do it my way, but it would be much better if I actually had a virtual assistant.
So virtual assistants, to answer your question, right? Like we'll start out doing really simple things and then become more and more competent. Another example that you may have encountered is the Gmail autocomplete function, right? Where you start to type an email and then it finishes it for you. And you realize that 90% of your emails really don't require the use of your brain, right? So instead of the email just being ignored, it gets sent oh, hey, let's blah, blah, right? And, sounds very affectionate, right? By the way, the guys who did this project at Google, there was a phrase. In the beginning, things were not working very well because there was a particular phrase that it just put in every email. You know what it was?
Hey, man.
I love you. Right? I love you, I love you, I love you. Always, was always a good solution. And then they had to cut back on that. So there you go. Yeah.
All right, one more question. The gentleman right here in the middle had been waiting for a while. So could we get the mic up there?
Based on your earlier statement of artificial intelligence and being competitive advantage, correct? And if you've reflected upon socioeconomic environment, business, political system, data sharing. So, and this is just, paying devil's advocate. Looking at smart cities, correct? Singapore is one of the most advanced. Looking at artificial intelligence, where China is gaining an advantage. Does it mean that command economies are better at artificial intelligence and will have a competitive advantage compared to free economies? And
This is a great question, I think our thinking of this has evolved dramatically in the last 10 years. 10 years, I mea culpa, right? 10 years ago, if you asked me, said like, AI, machine learning, these are the greatest tool ever for democracy, right? The representatives can become more responsive to you. They can ask, your model, right? They can ask your recommended system, which policies do you prefer? What do you want to do in the city today? In fact, there's a lot of great experiments like this happening today. So I think, AI has enormous potential to make democracies better, right? Today, like the number of bits per year that you communicate with your representatives is like, what, 100? This is like ridiculous, right? This is like 19th century, right? All of this should change, right? However, the progress of making democracy better with AI has been remarkably slow. Partly because there are a lot of entrenched interests against it. So for example, I was talking recently with someone in the European Parliament who's, one of the leaders in the whole tech area. And he was like saying like, we should have an agent like this, Europa, like to ask questions about governance and whatnot, and said like, yeah, and this would be really great for like, the people in the European Commission and members of the European Parliament because, they will be in better contact, right, with their constituents. And they said like, but they don't necessarily want to be in better contact with their constituents. They prefer to be able to ignore them, right? So the challenges for democracy. On the other hand, right, on the side of autocracy, the thing that I think is now very clear that we were kind of neglecting 10 or 20 years ago is that AI is possibly the greatest tool ever invented for the autocrat, right? AI is the ultimate surveillance system, the ultimate bureaucrat that has no conscience, keeps tracks on everybody, right? Doesn't get bored, right? If you're an autocrat and you want to oppress your people, AI is for you. No wonder Vladimir Putin is big on it, and Xi Jinping too, right? By the way, the way he was found with this is interesting, is that like he gives a New Year's address every year, and the belief is that they deliberately put some books in the background on his shelf to send a message that this is what, the leadership thinks is important right now. And in China, this really matters. And they are going all out with AI, largely for benign reasons, right? And we should all be in favor of those, right? Both for the Chinese people and for everybody else. There are more people doing good things. But they're also going all out building a surveillance state based on AI, right? With their social rating system, right? Which, is very embryonic, but is really scary. With their whole network of surveillance cameras, right? AI can be watching everybody all the time, right? And in fact, there was like this, to just complete that thought, I saw this very good interview that, I forget where it was, but like the journalist interviewed one of the people who were running the system, right? And the journalist at one point said like, but this stuff of like, you recognize people's faces as they cross the street and whatnot, this doesn't really work yet, does it? And the Chinese official very calmly said like, no, but that doesn't matter. All that matters is that people believe it works and it does its job, right? It's like God, right? God is watching everybody, so you better behave, right? So to answer your question, I think we are going to find out who AI works better for. And because it works, it helps everybody. AI is a tool of immense power. Every technology gives you power. AI, I think, is unusual in just the sheer scale and firepower that it gives you. Democrats and autocrats will both try to make use of it. We should not prejudge how this will end. I think and I think and hope, but we have to make that happen, is that in the end, democracy will win, but it won't be democracy like we have today. It will be democracy transformed to work better with AI. And in the meantime, there is a race going on, and we should, face that fact. Exactly, yeah. I mean, I don't know if you guys saw this recent book by Kai-Fu Lee, right? He says like, here are the key advantages, China has in AI. One of them is they have all the data. They're not worrying about privacy, right? They can experiment with whatever they want. And in fact, I often worry that we in the West are in the process of hamstringing our tech companies because we're worried about them becoming too far, which is a genuine worry. But then they're going to go up against the Chinese tech companies, and those have no such problems. And they're, like, they don't have the option of not collaborating with the government. Right here, the workers will say like, no, we don't want you to take part in, in defense-related projects. We refuse to collaborate. So yeah, so autocrats, but if you look at history, things always start out looking like they, looking better for the autocrats, right? If you reverse, if you go back to like 100 years ago, things were looking very good for the autocrats, right? Not very good for the democracies. Now what will happen? One dark thought is that maybe autocracy will prevail, not because it's better, but because China's bigger. Some people say that democracy prevailed in the 20th century, not because it was a better system, but because America, who was the most powerful country with the biggest industry, happened to be democratic. I don't buy that. I think America was powerful largely because of democracy and, private ownership and all that stuff, but we'll see.
I'm going to call an end to it since we're over time already. Thank you so much for coming. Thank you, everyone, for being here. A small token of our
Thank you.
appreciation. Yeah. Thank you, everyone. See you in a couple weeks.